Okay, so that's the polytope, right? So let's try to compute all its facets. So so what is the A matrix? So remember we have to label them V1, V2, V3, V4, V5, V6, V7, right? So it has 7 vertices. So what's the A matrix? So in the first row we have all ones. So let's just write this down. So we have 1, then 4 zeros. So this is E1, E2, E3, E4, and then 2, 1, 2, 1, 1, 2, 2, 1. Right? And so this is, so D is 4, N is 7, right? So there are 7 vertices. So what is the size of B? So B should be n cross n minus D minus 1, right? What is n minus D minus 1? It's 2, right? So we now have, so this is our B. So that is 7 cross 2. Okay, so let's try and work this out. So we have 3 dimensions. So we'll make these last 2. So that's a standard trick that will always work?
It will always work.
Okay.
Because the basis it's a basis, right?
Yeah.
So I can always make the last part.
So if this were like 3, then I can put the 3 identity matrix. Okay, so this is a useful trick.
You can. Yeah.
You don't have to.
You don't have to.
Yeah.
You can.
Okay, so we'll do the same choice as before.
I think the thing I gave you is just the other way. 0, 1, then 1, 0.
Okay, yeah, doesn't matter. We'll do it. Yeah. Okay, so now we want to find, so there are 5 entries here. So we want to, so they should sum to -1 in both cases. That's one equation because of the first row. So let's look at B1. So let's solve for B1. Let me call it B1. Oh, I shouldn't call it B1. Oh, because B1, D1, D2. Okay, so for D1, so solve for D1. Okay, I don't want to call it D1. Let's say alpha 1. Because I want to use ABCD for this. So let's call them ABCD. Right, so the first equation says what? No, the first equation. So it will say A plus C plus D plus E is -1. Right? Now let's look at the second equation. So it will say B, there's nothing C, nothing D, nothing E, plus 2 is equal to 0. So B equal to -2. So that's good news. We got one already. And here we'll have C is equal to -1. Okay, even better news. And D again is equal to -2. And D equal to -1. Wonderful. So the only thing remaining is A. So what is A? So A -2, -1, 2 minus 1 equal to minus 1. So that is 6 minus 1, 5. Okay. So that's the first one. So I'll erase it over here. So 5 minus 2 minus 1 minus 2. Oh, sorry. Yeah, minus 2 minus 1, 1, 0. Everybody got that? Okay. Now let's do alpha 2. The first equation is the same. So now this is A, B, C, D, E. And now it's again the same except that I put the last.
5 minus 1.
So now this is minus, oh sorry. So B is minus 1. C is minus 2. Right? 2 E is the same. Okay. So the problem is nicely posed so that we can get this quickly. And A is again the same because this is we've just interchanged to it. So 5 minus 2 minus 1. So it's actually this last vector only. The negative of that. Right? So it was nicely designed for us. Okay. And then we have to, okay, so now we have to draw, okay, so now we have these vectors. So this is B1, B2. We have to keep the same, so this was stressed that it's very important that we keep the same labeling as these. I mean, we don't change the labeling, right? So this has to be called B1, this has to be called B2, B3, B4, B5, B6, and B7. Well, transpose. Okay, so let's draw it. Okay, so now something interesting is happening that we have 3 vectors in the same line, right? So do they draw it as arrows or just points?
Arrows.
Arrows, okay. So let's draw, okay, I have to go all the way up to 5. And here minus I only have to go up to 2. Okay. So B1 is 5 comma 5. That is somewhere here. B1. B2 is minus 2 comma minus 1. So that is here. And B3 is minus 1 minus 2. Actually my figure is a bit actually exactly, yeah, that's what I should do. So this is minus 2 and I should go here. This is minus 1. Okay. So so minus 2 minus 1 is here. So that is B2. B3 is minus 1 minus 2. So that's here. Right? And then B4 is minus 2 minus 2. B5 is minus 1 minus 1. Right? And then B6 is 1, 0. Oh, should I use another color? Okay, too late. This is B6 and B7 is 0. Okay? Everybody got the same thing? Okay, so now the hard work of actually building. So we have to find, so from last time you saw that the facets are the largest in P. So we need to take the smallest collection of vertices which contains the origin here in the B side, right? So what are they? Can you? Right. So that's the fact that all three lie in the same line is very helpful. So the smallest collections containing 0. What are they? So 1, 4. 1, 4 and 1, 5. Anything else? They do. Yeah, because relative interior here is one dimensional. So relative interior means the interior of that line. Yeah, as a two-dimensional thing, it does not have an interior, but as a one-dimensional thing, it has. Right? So does it have only two faces?
No, then there are collections with 3.
Yeah, but
So these are some big facets.
these are facets of size 5. But, okay, so maybe I'll. So these are not smallest, but these are somehow minimal.
Minimal, yeah. So it's minimal.
So here I'll write the collection and here I'll write the facet. So here is 1, 4. So this corresponds to 2, 3, 5, 6, 7. And 1, 5. It corresponds to 2, 3, 4, 6, 7. Now we should not take anything that contains 1, 4 and add something. So we should not take 1, 4, 7. Right? If we take 1, 4, 7, that 0 will not be in the interior. Right? Because then it will be on the boundary. Right? So we should not take 1, 4, 7. It's okay? Or 1, 5, 7. So now we should start to take things. If we take 1, we should not. So we can take. Can you think of something that contains 1 and does not contain either 4 or 5, but contains the origin?
1, 3, 7, 1.
1, 3, 7. Yes, that's correct. So 1, 3, 7. So this corresponds to 2, 4. It's a facet. I mean, these are the vertices, right? So this will still live in 3 dimensions. So if you want, we can check. So 2, 4, 5, 6. Look at these 4 vertices. I claim that they do not. They don't live in 2 dimensions. They don't live in a 2-dimensional affine subspace, affine space. Okay, so 1, 3, 7. Very good. Anything else? 1, 2, 6. So there is a symmetry here, right? If I reflect about this line, the point configuration is symmetric. So 1, 3, 7 is there. So 1, 2, 6 should also be there by the same argument. 1, 2, 6. So 3, 4, 5, 7. 1, 2, 3. Yes, 1, 2, 3 is nice and symmetric. So 4, 5, 6, 7. So the general rule I was mentioning earlier is that you need at least d plus 1 points to span a d-dimensional space, affine space, right? So we should not be, no facet will be with 3 points. Okay?
And then except for 3, 4, 5, you take anything, you always get a children.
Take one.
And except for 5, you need from the 9, 0 to the
No, 1, 2, 4 will not work. 1, 2, 4 will not work.
4 and 5 you not take.
You don't take, okay?
Then 9,
1,
2, 7 will not work.
3, 6 will not work.
For the same reason, yeah. So it's not that simple, yeah. So with 1, have we exhausted everything? No? 173 we have.
137 we already.
167 does not contain the origin. Yeah, done, right? Everybody agree? With 1, we have exhausted everything. Okay? Just facets, yeah, we are only talking about facets. I mean, the question was only to find facets. Yeah, complete all facets. Compute all. Okay? Anything else? Okay, so now let's forget 1 and try to see if there are any other facets. 3, 6, 7, okay? 3, 6, 7. Wait, so I'll just write this. 1, 2, 4, 5. 3, 6, 7. Yeah, so 2, 6, 7 will also work for the same reason. 1, 3, 4, 5. 4, 6, 7. 4, 6, 7, 5, 6, 7. Just 1 second. 1, 2, 3, 5. 5, 6, 7. 2, 3, 4. Sorry, say that again.
No, but from the previous pages, if you replace 1 by 2 and 4, not the other one, 4 or 5. Replacing 1 by 4 or 5.
1 by 4 or 5? No, but
No, not necessarily.
yeah. 3, 4, 7 will not include. Yeah, that's a problem.
Either 6 or 7 should be there.
Both, I think both 6 and 7 have to be there. If one is not there, somehow if you just take 6 and the things below, then you will miss the origin. So you have to take both 6 and 7. And if you take both 6 and 7, we have listed everything. So it looks like we have all of them. 1, 2, 1, 2, 6 we have listed. 1, 4, 5. No, 1, 4, 5 you cannot have, no? I mean, okay, it's not a facet. 1, 4 is always, and 1, 5 are separate, correspond to facets. It's a face. 1, 4, 5 will correspond to 2, 3, 6, 7. That's a face, but it's contained in a facet.
So you can see what this is roughly, right? That if you take 1, 2, 3, 4, 5, you get a simplex coned with the origin, right? So you get, I can't draw it, it's in 4 dimensions, but you'd get something like this, but in 4 dimensions, right? So these are the unit vectors, and this is the origin. So if you convexify those, you will get 4-dimensional simplex in 5-dimensional space. So that's what's happening, in 4-dimensional space. So this, and this is easy. So then the complication is these two, right? So it's sort of like we are putting 2 more points that are beyond this facet. So like we're putting a point here and a point, another point there, and then we're connecting that to in all possible ways to this. I don't know, different ways, right? So you don't actually get this one. So the top part of this becomes very complicated, which is what you're seeing over here, right? So you should see these sides, the sides of the thing that looks like a tetrahedron. You should see the bottom, this side, and the back side. But this front face will get removed because we're adding 2 points on top and then convexifying over that. So that's roughly kind of the situation you should see here too. So for example, probably 1, 2, 3, 4, 1, 2, 3, 4, like this one is one of these coordinate planes, right? It's made up of the first 3 vectors. It's one of the coordinate planes. It's the plane where x4 is equal to 0, right? If you take the first 4. Anyway, it's nice. You can calculate these high dimensional things without being able to see it. Okay, so these are the facets. So this is what I mean by combinatorial polytope. So sometimes people will just say, this is the polytope. It has all these facets. But then your job is to actually, you might be asked to realize it, to actually find coordinates like over there. There'll be lots of ways to find coordinates over there. That'll do the job, right? Do you see how? Because, yeah, exactly. So this picture itself has a GL action on it, right? Because if I have a basis like this, and I can move this with any, not GL action, it has you can change bases, right? There are infinitely many bases for the kernel, so you can change bases here. Yeah, that is a GL action, right? So you can multiply the B on the right with some other matrix like H, which is invertible. It's still a basis. GL2 action, exactly. So I can multiply here with a 2 by 2 matrix, and I will get the same thing. I'll get a different basis. So there's a lot of different choices for this picture. All right. And but once you fix this picture, you still have some choices for this picture because it's just telling you that the row space has to be whatever is the orthogonal complement to this. So you have a lot of choices for this as well. That means you have a lot of different realizations of this polytope. And yeah, so if somebody just gives you that data, you can construct this picture, but then you still have infinitely many choices for this picture. And it may be that you can't realize it with certain extra properties, like integer vertices or rational vertices or things like that, okay? All right. So, when do we stop next? 3:15, okay. Yeah, you can go backwards, exactly. It's not unique, correct. It'll give you the same combinatorics. It'll give you the same collection of facets, but it may be a different embedding, right? Like for example, if I take the square, then its facets are 1, 2, 2, 3, 3, 4, 1, 4. But this is also true if I take this picture and put 1, 2, 3, 4 here. Combinatorially, these two polytopes are the same. They have the same collection of facets in this notation. But embedding-wise, they're very different, right? So these are, so in this example, they are off by a projective transformation, right? Yeah, because we didn't preserve parallel, no, something, right? Is it projective? Not even projective, maybe. Yeah, so they're combinatorially equivalent. That's all we can say, right? So any kind of, so you have different types of transformations. You can have affine transformation, that just means translate, rotate. That is a type of translation. You can have projective transformation, but their parallel things should stay parallel, right? So is that true? Am I getting confused? What is projective? Incidences should stay the same? Okay, I'm getting confused. Anyway, never mind, okay. So there is something called combinatorial polytope, which just means giving this information, nothing else. You're just told what are the different things that should form facets. Right. So that's this example. All right. So we could talk a little bit about designs for a while. We could also prove this lemma. Maybe we wait for the next session to prove this lemma. So let me come back to designs a little bit and connect it to this theorem. Okay? That's really our next goal. So I'll leave the lemma there so that we can prove it later in the last session. Did anybody think about why no, okay, maybe I'll have to put designs back in. But remember I told you yesterday that no proper subset of vertices can average all the eigenvectors of the Laplacian or the walk matrix or whatever. Do you see that? Do you see why that's true? Did anyone think about it? So let me put back the definition of design, and then I want to think about that for just a little bit. Okay, so we are back to graphs. So back to graphical designs. Okay, so we have this graph G, which has vertices 1 through n and some edge set. Okay, so let me remind you what a design is. Okay, so pick one of these matrices that we've talked about, Laplacian or walk matrix or adjacency, whatever you want. In different examples, I might switch around. But for today, let me just take L. Okay, so I'm picking the Laplacian of this matrix. Yeah, everything is deregular. Okay, so don't. You can make this theory work for non-regular things, but it gets more messy. So let's not worry about it. Okay, so I think in the slides that I'm going to show next, we are taking AD inverse or 1 over dA. So I don't mind which one you pick, but pick one. Okay, pick one of these matrices. And no matter which matrix you pick, it has eigenvalues. So these has the eigenvalues lambdas, these had eigenvalues taus, and these had eigenvalues mu's. Right, this was our convention. And they were ordered in different ways depending on which matrix you got. But we definitely had this orthonormal eigenvectors. So all of these guys have orthonormal eigenvectors, which we call phi1 through phi n. And this first one is always the 1. Okay? So this is the trivial eigenvector. This is always 1. It's a connected graph, so the second eigenvalue is positive. So the first eigenspace is just the span of 1. Okay? Nothing else is in the span of the first eigenspace. Okay, so pick one of them. Okay, I'm not choosing, but pick one. And then what we were trying to do is the following, right? So we have this, we organize the eigenvectors. Let me just organize them into a matrix, which we will call U. So this is phi1 transpose. And then I have phi2 transpose up to some number, say phi L transpose. And then after that, I have the rest. I go all the way to phi n transpose. Okay, so I'm putting all the eigenvectors in the rows of a matrix. So this is some n by n matrix that is definitely full rank, right? Because these are independent vectors. So this is a full rank matrix that I can invert if I want, but we won't. Okay, so this is what we have. Okay, so then what is the design, right? So we can, okay, as long as you put the very first one in the top, I don't care how you order these other ones, okay? So let's order these whatever way we want. I fix some ordering, good? So then what I wanted to do is the following. I want to pick some collection of these eigenvectors. So let's say phi2, phi3, up to phi L. All right, so I take the ones that I want to average. So the ones I want to average are everything that's sitting in this block from here to here. So this is the one I want, these are the ones I want to average, okay? So how do I want to average? So what I'm trying to do is I'm trying to put, this is my graph, let's say, they're numbered, 1, 2, 3, 4, 5, 6, these are the vertices, okay? So what are we trying to do? We're trying to find a subset of these vertices, so maybe this one, and that one, and that one, okay? This is a subset W inside N. I'm trying to find a subset with weights. So I'm also allowed to put a weight here, which I will call A4, and a weight here, or let's call it W4, and I'll put a weight here called W6, and I'll put a weight here called W2, okay? And all the other weights are 0. So all these other weights are 0. So I can think of the weight vector as an n-dimensional vector, thank you, that has only positive weights on the things that I picked. So I want to pick a weight collection like that. And remember, once I give you the weight vector, the big W is clear, right? Because I just have to look at where are these weights positive. That's exactly big W, okay? So W really carries all the information, right? If I give you W, so I'm going to call W a design. It contains both the collection of vertices I'm picking as well as the weights I'm putting on those vertices, okay? So W is what I'm going to call a design.
So when you say W, you mean small w, not?
Yeah, oh yeah, there are, okay, that's not a good notation. Okay, let's go back to A. I think this is what we were using before. A. Okay, let's use A. So A is some vector that has entries A1, A2, up to AN. This is a weight vector, and let's assume they are non-negative, okay? For today, I'm going to mostly assume they are non-negative. And the big W is just the support of this A. Okay? So it's in lots of places I want this A vector to be 0. And wherever it's not 0, it's picking out some vertices, okay? So what does it mean to be a design? So I know what I want to average, and what I want is an A vector such that it should, when I compute the average, when I take the weighted average of a phi that lives in this big collection phi, okay? So the big collection phi is the yellow collection. This is phi, the big capital phi. So whenever I pick one of these yellow eigenvectors and I take the weighted average of that phi with a W, okay? So everywhere this was 0, there's no contribution. I want this to come out to be the global average of this phi, okay? Which is 0. Remember we argued that, so I want this to be the global average, which is phi transpose 1 divided by n, if you like. That's the global average. But this is just 0 because phi is orthogonal to the all ones, okay? So what we really want is the weighted average to be exactly 0 for every phi that's in this capital phi. Is this okay? This is what I'm going to call a capital phi design. So we will say, such that this, then call a capital phi design. This is okay? This is the definition of a design. So we're looking for a collection of vertices with non-negative weights and such that for whatever prescribed number of eigenvectors, the weighted average is the global average. Good so far? Yeah. Sorry, louder?
Are we not counting out the support?
How the support?
Yesterday they were calling it a 2 design, 3 design, based on the support.
Yeah, no, yes, okay, we'll come back to that, okay? The 2 design, 3 design was not quite the support, but it was a number of eigenspaces we were averaging, okay? So here I'm making it a little bit easier. I'm not distinguishing by eigenspaces. I'm just saying take some collection. And yesterday we were saying that the collection we want to take should not cut through any eigenspace, right? So maybe the one eigenspace is this, and then the next eigenspace is this big one, but I don't want this bottom cut to cut through an eigenspace, okay? So that's what we actually want to do in practice, because it's complicated if we don't do that. It's not complicated, it's just more messy, but there's nothing wrong in this definition. We can pick any collection of vectors and say I want to average them, and I want to find the W's that average them. Is this okay? So this is the definition of a capital phi design, okay? Non-negative weight vector such that weighted average is global average for every eigenvector in the capital phi.
We also want the sum of the AIs to be 1, because you want it to also average phi 1.
Yeah, so you could normalize it, yes. So whatever if we also do want to average phi 1, so let's see what happens to phi 1. So if I do phi 1 transpose A, then this is equal to all 1s transpose A, which is the sum of the AIs, right? So this comes out to be something positive. I don't know what it is. It's something positive. And we can always assume, if we want, we can always divide, yeah. So ideally we could divide the A by the sum of the AIs, and then this average will become 1, okay? So we could normalize it. So we don't worry about phi 1, okay? Whatever we choose for the others, we can make it work for phi 1. So phi 1 is not important in the whole thing, okay? Every subset will average phi 1. Anything you give me will average phi 1. I just need to normalize it, right? So why is that? Why it won't mess with everything else, because this is 0, right? So no matter how I scale this, I will still get 0 here. That's what's saving us, right? So as long as I find a solution here, I'm good. Everybody okay? And then yesterday we showed by Farkas lemma and so on. So we are showing that, so the system we are solving is capital phi times A is equal to 0. A is non-negative. This is what we are solving, okay? And yesterday by Farkas lemma we said this always has a solution, and in fact it has a solution of size at most the size of L, the size of phi, okay? So there exists a solution of support size at most L, okay? So we argued this yesterday. So this is a graphical design, okay? All right, so now comes the fun part. How do we relate it to this theorem? Let's try to relate it to this theorem, okay? The Gale duality theorem, second one. Okay, so do you see that condition, right? Phi A is equal to 0, A non-negative, forget about the support for a moment. Does it look like either this or this?
For the sum to be 0, 0 must belong to the relativity.
Yeah, right? So what is this condition telling us? Let's reinterpret this condition, right? This is saying that 0 lies in the column space of phi, right? And it's something non-negative, and I can scale it to be some 1. So let's do so I can always assume that without loss of generality, we can assume that the sum of the AIs is 1, because scaling doesn't destroy the solution, okay? So let's just assume that. So now what I'm getting is that 0 lies in the column space of phi. So 0 is a combination of the columns of phi. That's what we get from here. But if we also add this, then what are we getting? And this. Yeah, so if you add this piece and this piece, you're getting that 0 lies. So if I take this much information, then I'm getting that 0 lies in the convex hull of the columns of phi. Do you agree with this? Yeah? So the first piece is just telling you 0 lies in the column space of phi. but A is non-negative and the sum of the AIs is 1. So that means 0 is actually a convex combination of the columns of phi. Okay? So columns of phi are just some vectors. So the columns of phi are, so remember the rows are the eigenvectors, okay? So what I'm doing now is looking at the columns of this. So we're looking at the columns of this matrix. All right? And those columns are these red vectors. So they are like whichever way, okay? They are like that. And we are getting that 0 lies in the convex hull of the columns. 0 lies in the convex hull of the columns, right? But 0 has, I mean, this A vector has can have very low support, right? So what is where does it actually lie? It doesn't need all the columns of phi to be in the convex hull, right? So can we modify this slightly better, make it slightly better? Not just convex hull of columns of V. It's in the convex hull of, yeah, it's in the convex hull of only those columns that come with positive weights, right? So you only need the columns that correspond to the support of A, okay? So this lies in the columns, convex hull of columns of phi indexed by the support of A. This is what we actually can conclude, right? So some of the A coordinates are 0. So so for example, if the A coordinates, if my A vector was, running out of colors here. So if the A vector was, say, 0 on this, 0 on this, and the A vector is like something non-zero here, something non-zero here, something non-zero here, okay? This could be how the A vector looks. Then I'm just getting that 0 is in the convex hull of these 3 things. The others are not being used, right? Because those are like 0 times the columns that have 0 on it, okay? So really it is true that it's in the convex hull of all the columns, that's true, but this is even better. It's actually in the convex hull of the columns that are indexed by the support. Just a few columns, okay? So 0 lies in there, good? Okay, great. So being a design is the same thing as saying this. 0 lies in the convex hull of the columns indexed by support of A. Okay?
But the definition of a phi design, you don't want support of A to be less than equal to L?
It can be less than L. It can be L. No, we don't decide that. L is sort of a guarantee on the size of the designs, right? It's a guarantee that there are designs of size at most L. Okay. But we don't care. The design can be big. Okay? We don't care how big the design is right now. Okay. So my definition just says this much. Phi A must be 0, A must be non-negative, sum of the AIs is 1, that's a normalization. And that translates exactly to saying that 0 lies in the convex hull of some of the columns of this yellow matrix. Everybody okay? All right, so let's go. So that's this. This is the yellow piece. Okay? So what the role played by BI here is played by which, the row vectors or the column vectors? Yeah, the red column vectors, right? Because this is saying 0 lies in the convex hull of some BIs, and we just said that being a design is the same as being in the convex hull of the columns of the phi matrix. Those are the red columns, the red guys, okay? So the phis are rows, but I want 0 to lie in the convex hull of the columns of the yellow part, okay? So maybe there's something non-zero here, there's something non-zero here, and there's something non-zero here. Everywhere the A vector is just 0. Okay? That's how the A vector can look. Everybody okay? All right.
This may not be the relative interior, right? I'm still confused. Because
Yeah, it's relative interior because we are only picking the, if we pick the support away,
yeah.
right? So if I'm only choosing the columns that have a positive weight on it, then 0 is in the interior. Do you agree with this? Yeah? If I take also the things that have zeros on it, then I don't know. But if you, because we are guaranteeing that we are only making a combination from the positive parts of A, where there is something.
So you 0 belongs to convex hull of the columns of phi, I understood.
Yeah.
But then in the next step you are writing index by support of A.
Correct. So yeah, let's do it a little bit better. So what does this mean, right? This means that A0 is equal to sum of phi1, so those columns, we need a name for those columns. So what shall we call it? Yeah, let's call them C1, C2, and so on. So these columns are C1, C2, up to Cn. There's always n of them, right? So 0 being in the convex hull of the columns means that 0 is equal to A1, C1, plus A2, C2, plus up to AN, Cn. And I also have that the AIs are all non-negative. I also have that the sum of the AIs is 1. Okay? So 0 is a convex combination of C1, C2 up to Cn. But some of these AIs are 0, right? Could be. Maybe none of them are. But if some of them are 0, then that contribution just goes away. So if this is 0, this contribution just goes away. Maybe another one goes away. And maybe another one goes away. So all I'm left with is a combination of the columns where the AI was positive. Okay? That's what I mean by 0 actually lies in the convex hull of only those columns indexed by the support of A. Okay? We don't need all the columns. We just need the ones indexed by the support of A. But those are all positive, they're positively combining a bunch of vectors to give you 0. So 0 really is in the relative interior. Okay? Okay, so being a design is the top part of the Gale duality theorem. Okay, so then can we interpret the second part? What is the second part telling us? Okay, I think I can erase something here. Let's start erasing something here. Okay, so what should happen in the second part? In the second part, I want to say, okay, if 0 lies here, that means A is a design, according to what we just said. Then the convex hull of the VIs is a face of P. Okay, so there's some polytope, that's the convex hull of VIs, and you'll see its face will show up. Okay, so the next question is, what are these VIs? So these guys, these columns, actually we should call them Bs, right? Because they're like Bs. So let's call them Bs instead of Cs. So these columns are Bs. B1, B2, Bn. Okay? So these are columns and they are Bs. Okay? So in Gale duality, remember the Bs are coming from the B matrix and these are the rows of the B matrix. Okay? So we're taking this yellow matrix and just rotating it 90 degrees, and I get that. Okay? And now we have to search for a matrix A that sits here so that this whole thing will be 0, right? And they should be like nice in the sense that the row span of the green must be the kernel of the, row span of the green must be orthogonal to the column span of the red and all that, okay? So all the ranks and all have to work out. So what do we need to find? So these yellow, no more yellow, I think.
There's no chalk.
Oh, there's new chalk, okay. Okay. All right, so I just took the yellow thing. Okay, I'm going to make this even nicer. Let's make this nicer. So this yellow piece rotated and became this.
Transposed, right?
Yeah, 90 degrees. Yeah, transposed. Exactly, transposed. Okay, so this is the yellow piece. And its rows are now those red columns. Okay, these are the BIs. BI transpose. Good? That's what happened. So we just extracted the yellow, transposed it, and then took its rows, which is the same as the columns from the original. Okay? So how do we find the A part? I want to find now something here such that this multiplication will give me 0. So I want to find a bunch of rows that are green that's going to be orthogonal to all the yellow columns. Okay? The columns of yellow are eigenvectors. Sorry. The yellow rows are eigenvectors from here. So do you see what the green part is? Not AIs. Okay, I can't hear anything, so maybe one person at a time. Okay, I just need to find some things here so that all these green things are orthogonal to all these yellow things, right, which came from here. That's what duality does, right? So yellow eigenvectors we have already in the U matrix. What's orthogonal to the yellow eigenvectors? All the other eigenvectors, right? All the other eigenvectors are orthogonal to the yellow eigenvectors. And do we have the right number? Yes, we have exactly the right number because this is an orthonormal basis, right? So if I take the span of the yellow rows, then exactly orthogonal to that is the span of all the other rows. Okay? So the A is sort of sitting for you for free. This is the A part. This along with this. So this along with this is A. Do you agree with this? So if I take the green, so the top row is always going to be 1 because it always has the very first row. And then the rest of it, this part, is going to be the other green things. But altogether, this is phi bar. Okay? This is everything that's not yellow. That's the A part. Everybody okay? So we have a dual configuration for free sitting inside the original eigenbasis matrix. Okay? I picked out some things to average, that's going, and then I rotate, that's going to be the B, and then everything else is the A. Good? Okay, so what polytope are we talking about? We got the A. This is A. This is B. And this is equal to 0. Okay, so what's the polytope we should be constructing? Yeah? So the polytope we want is the convex hull of Yeah. So we have notation here. Columns of which one? A. Right? So we want to convexify these columns. Do you agree? So the polytope is going to be the convex hull of the columns of phi bar. Okay? So I take the columns.
In phi bar, are you including all one also?
Yes, yes. Because remember, otherwise we won't get, the all ones does not have global average 0, right? I want global average 0. So I'm only taking phi2, phi3 up to phi L. All ones we leave out. So I have to include it now in the other one to get the rank to work out, right? If I want the left kernel of this matrix, I really need everything that I did not take in the yellow. I need the all ones and all the other greens. Everybody okay? Right? Okay. So a design means being in the convex hull of the rows of this B matrix. That's what a design means. So that means every design corresponds to, by the theorem. So if I have 0 in the convex hull of the red rows, Yeah, so it corresponds, its complement will be a facet or face of the green polytope. Okay? So this polytope is coming from the green. This, let's call it P. So what we conclude using that theorem is that, so let me write the theorem and we're going to look at lots of examples. So the result is that A is a phi design if and only if n minus the support of A. So remember, A is supported on some vertices. That's all we're really caring about. Okay, there are some weights there too. But n minus the support of A is a face of P, where P is the convex hull of the columns of phi bar. It's phi bar. Okay, we'll do lots of examples. Yes, Anissa.
So, I bar is the small green submatrix, no, without the 1, 1, 1.
No, with the 1, 1, 1. Why? Let's think about that. Why?
Then we add 1, 1, 1 artificially when we.
Oh, yeah. It doesn't. So it's true we are adding artificially, but it's really the same polytope, right? I just lifted it to one higher dimension. So let's be generous to it, right? We give it the all ones. It's still the same polytope. Is that okay? There's no problem. Yeah.
I'm going to find this matrix A. When talking about other eigenvectors being perpendicular to it,
Yeah.
there are a few rows that we lost, right?
Which rows?
By support of it.
We lost some columns, maybe.
Yeah, the columns, those entries won't be affected.
No. So, okay. So, A was, so there are two things going on, right? This is some particular A that satisfied, this is a solution to the system. The system has many solutions. The only thing constant here is this phi that we picked, okay? So, if I have an A that satisfies this, then I'm getting some collection of the red columns that contain 0 in the origin. If I pick a different A, I get a different collection of red columns that have 0 in the origin, okay? So as I pick different A's, I get different collections of the red columns that have 0 in the origin, okay? So that is like the top part of the theorem because it's saying 0 lies in the relative interior of the convex hull of some of the B's, okay? So let's look at all of the B's, which are all the red stuff. And then once I know all the B's, I can look at what should be my A. Right? So every time I pick a A here, I'm getting 0 in the convex hull of some red columns, and I'm getting a facet or face on the other side. If I change the A, I get a different face. Do you agree? So the only constants here are, the things that are remaining constant all the time is the choice of phi, and therefore the choice also of phi bar.
So what one is the support of A less than equal to L plane? At this moment, nothing, right?
At this moment, nothing. Yeah.
Dimension B is n by L, right?
Dimension what?
Dimension of B, the matrix B in this process.
Yeah. Yeah.
All the columns of P2 to PL.
Exactly. So this,
N by L minus 1, right?
yeah, n by L minus 1, correct. That's the yellow part. Make it yellow. N by L minus 1. So then this should be n minus L minus 1, okay? So it should be L minus L plus 1 times n. That's the size of that. Correct, okay? It has this extra all ones. The extra all ones is important to make this theorem work, right? The theorem really needed the extra all ones, Gale duality, right? And we're really lucky we have this all ones just sitting there that we're not trying to average, so throw it in with the complement, and we get Gale duality to work. Sorry? Relative interior part, meaning, oh, why is it in the relative interior? Okay, so, okay, let's go back here. So we'll do examples, and then you'll hopefully see more things. Yeah?
Is P
Full rank n by n, yeah.
So whatever we are getting A, that is upper part is 1 all 1 and the green part down there. So if the dimension of the lower green part is D, then adding all 1, since all of these are orthonormal eigenvector, so it's full rank. So if we add these with this, then dimension will increase.
Correct.
So your answer is like D plus 1, rank of this matrix is D plus 1 after adding all 1.
Yeah.
That can it imply from here?
No, because these are very special, right? These are eigenvectors, they're orthonormal and all that,
Special
right?
case.
Yeah, it's a very special case. So if in the previous case, we just took any polytope, put 1, 1, 1, and then V1, V2, V3, and I'm saying the rank is still D plus 1 if the polytope was D-dimensional, otherwise no, okay? Here, if you use those green columns as V1 through Vn, that's a pretty special choice because it really is coming from an orthonormal. Okay, it's not actually a special choice because there's a theorem by one of my students who proved that every polytope can be realized as the convex hull of these green things, the columns of the green things, okay? So it's actually not that special. I might mention it again later. So this polytope P is what we call universal in the sense that there is, no matter what polytope you give me, there is some graph and a choice of eigenvectors for which I can take a piece of the U matrix, convexify the columns, and I'll get that polytope back. So these are called eigenpolytopes, by the way, so let me give it a name. So this P is called an eigenpolytope because it's coming from this eigenvector construction. And this was, a version of this was defined by, the basic version of this is due to Gotzel, who is a very famous graph theorist from Waterloo. And he defined something that's slightly more restrictive than what I'm telling you, but it's really his definition, okay? So these are called eigenpolytopes because we are taking some eigenvectors and convexifying their columns. Yeah? Okay, so what the student proved, my student proved is that every polytope is affinely equivalent to an eigenpolytope. So eigenpolytopes are universal, they're not that special. Yeah. So in a way, you're right. The argument you gave is correct, but it requires some transformations. So she was asking that, is this the proof that the A matrix always has rank D plus 1? Remember before, in the beginning, like last session, we said that when you construct this polytope, where you put 1s here and then you put the V's here. Remember I said that this, even though this is D-dimensional and this is 1, I said that the rank is D plus 1. And you can clearly see it here, right? Because whatever is the thing here, you have to add this, because these are all independent rows. So you can clearly see it here. That's what Aditi was asking. Yeah? So it's true. It's true in this meta sense. Yes. But the other one you can prove without much work. Okay, back to you. Okay, you want to know about the relative interior, right? Okay, so I think if I'm understanding your question, it's this picture. Okay, so let's take this example again. Okay, so let's take a Gale, some kind of Gale dual, right? So I have some red vectors. Here are my red vectors. Maybe even this is even doubled up, okay? So these are the red vectors coming from the columns of the yellow piece, okay? And now I'm choosing, I have some A where all of the red vectors will sum up to 0 if I weight it, right? So maybe my A1 is, so let's write the A in maybe white. So maybe this is saying if I take 2 times this minus plus 3 times this plus 1 time this, I will get 0. And I don't need this and I don't need this. Okay? So it could be my A vectors like this. Do you agree? It has these coordinates, right? So I'm never going to use this vector that has 0 weight and this vector that has 0 weight. But I'm using 2 times this vector plus 3 times this vector. Let's make it half and a third and say 1 or something. And yeah. 1/6, yeah, I have to do that. So then I'm getting, so there's some scaling, let's assume we've already scaled it, and we're seeing that 0 lies in the relative interior of this, okay? So 0 lies here. Now, you see, because all of these are positive, right, there's something sticking out from all of them, and 0 cannot end up being in the boundary of one of this, right? Like if 0 was here, then it's only using this and this, not this. But this is part of the convex combination because that's how the A vector comes to you. It's telling you it's positive here, here, here. Does that answer your question?
You could have in high dimensions like the reader.
Sorry?
High dimensions, like for example, you could have like one normal vector and two.
Yeah.
Some look off.
Uh,
You're not adding any weight for this. Let's say you are having 3 vectors.
so, okay, I think, yeah, but then you wouldn't use that, right? So I think maybe we should just start looking at examples. So you're worried about some situation like this, and you're taking the convex hull. Is that what you're thinking about? But really, this is redundant, right? 0 is already in the convex hull of these two. Once you remove this, it's in the relative interior, right? So you have to look at the affine hull of what you currently have, and in that affine hull, this thing has an interior. That's why the relative interior is there. You remove it, like you don't need it, right? Yeah, yeah. You might as well use a smaller A, right? If those 3 worked, then the 2 will also work. Let's do I think we should see an example, and that might help. But is the theory clear? How the Gale duality theorem plugged into the world of designs? Yeah? Okay, you want to see an example? Okay, doubting Thomases. Okay, so did you think about why no proper subset can average everything? So can it be that phi A is 0, where phi is like everything, and A is non-negative? Okay, let's start with this one. I think this is one of the easier ones to see. Okay, so this is a graph called the truncated tetrahedral graph. You can see why. It's a tetrahedron with all its corners chopped off. Okay, and that's the graph of the polytope. Do you see the corners that would have been there? So it's a tetrahedron where you chop off all the corners. Okay, it's called that. Okay, so this is the full set of eigenvectors for this matrix, so for this graph. This graph has how many? 1, 2, 3, 4 times 3, 12 vertices, right? 12 vertices, so there should be 12 columns and 12 rows, right? These are all the eigenvectors, good? And I'm choosing to average all the blue, okay? Let's try to average all the blue. So by our theorem, we should take the pink part, we should convexify the columns, read off the facets, and then go back and figure out the designs, okay? So let's take the pink part. The pink part is really nice, right? Because it's essentially 2-dimensional. It's just got these ones on it. That was Anis's comment. So it's really a 2-dimensional eigenpolytope that I'm going to construct. Okay, so let's construct it. So those are all those rows. There's the all ones row and those bottom 2 rows that were pink. Okay, so it looks like it's a 12-gon when you look at it first, right? Because there are 12 columns in 2 dimensions. The 1, 1, 1 you can ignore when you're drawing the picture. But if you stare at it, you see lots of columns are doubled up, right? All the pink columns are the same, the blue columns are the same, the yellow columns are the same. So when I take the convex hull, it's not a 12-gon, it's actually a triangle. Yeah? So it's a triangle where all the pink is what? Column 1, 6, and 7, right?
And 11.
And 11, yeah. So 1, 6, 7, and 11 go to 1 point, which is the point 1, 0. And then all the yellows go to 0, 1. And all the blues go to -1, -1. Okay? So the eigenpolytope is a triangle. Okay? So then I can see its facets, right? So for example, 1, 2 is a facet. Sorry, how should we think about this? No, you have to take all the indices. So yeah, let's pick this red facet. We already have one colored here. So on this facet lives vertex 1, 6, 7, 11, 3, 4, 9, and 12. All those vertices live on this facet, right? So the complementary index, which is 2, 5, 8, 10, should give us a design. It should give us an A vector that's going to be in the relative interior of the convex hull of the vectors that we tried to average. Okay? So
A is being used to the, I mean 0 is in the relative.
0 is in the relative interior, sorry, yeah. So here we're using this theorem to first construct the polytope. So we're using this part to figure out the designs. The designs come from this part, okay? So the polytope is nice, it's just a triangle. And it has only 3 facets. So so one design is going to be 2, 5, 8, 10. That means 2, 5, 8, 10. So that means I can put weights on these vertices. And I'm not telling you what the weights are, we have to solve for them. But you can put weights on those vertices and average all those blue eigenvectors that yeah. So there is a design of size 4. What are we averaging? All these blue guys will be averaged by, let's check, 2, 5, 8, 10 will average all the blues, okay? So maybe, where did we go? Yeah, 2, 5, 8, 10. So 2, 5, okay, a little bit hard to see. But if you take the columns 2, 5, 8, 10, then there is a positive weight you can put on those, that'll give you 0. Make sense? Okay, so in this example, what are the minimal designs? Why am I going backwards or forwards? Forwards, yeah. So it has only 3 facets, right? So I get one design from here, the complement of this facet, one design from here, complement of this facet, one design here, complement of that facet. So there are 3 minimal facets, minimal designs. Okay, facets are big, so they correspond to the smallest convex combinations in the B side. So these are the minimal designs. These are the minimal number of vertices of the graph I need to put weights so that I can average all the blue stuff. Okay?
Just to clarify, you could have gotten another design which does the same thing if you just took 3, 4, 9, and 12.
Correct. If you 3, 4, 9, and 12 is also a design that would have averaged all the blue things. And 1, 6, 7, and 11 will also average all the blue things. Does this make sense? So if you wanted some bigger designs, what would you look at in the triangle? These are so the minimal designs seem to have size 4 in this example, right? But if I took only this dot, this is a face, right? So then what would be the design that corresponds to it? Yeah, you need the blues and the yellows. Okay, so that's some big design. You need to put weights on 8 vertices to average the blue vectors. But why would you do that, right? When you can do 4. So we want minimal. Okay.
What are the weights?
Yeah, weights we have to, yeah, so there is a nice way to see what the weights are. So what the weights essentially are, no. So what the weights are is essentially, let me think about it. Yeah, okay. So it's a little hard to see in the triangle, but in general, if the polytope was, bigger, so let's say instead of the triangle, I had something like this, and so I know that this is a facet. So I know that the weights are, these are the vertices that are going to carry the design. The complement is going to carry the design. So what you do is, okay, without any proof, I'll tell you what you have to do. So you take this span of the facet, and then you start making parallel translates of it. So maybe this is a parallel translate, this is a parallel translate, and this is a parallel translate. okay? And the weights are going to be 0 weight on these guys, because they're not part of the design, right? The design is the complement. 0 weight on this, weight 1 on this, weight 2 on this, and weight 3 on this, roughly, okay? So you have to be a little bit more careful. But it comes from the various, it's the level sets of the affine span of that facet as you sweep it through this polytope. It's very, very pretty. Yeah, it's very, very pretty. Okay, very good. Let's undo the question.